Hi. So in this session I want to talk about space complexity. So far we have talked about time, right? We have seen how to calculate time complexity. Finding space complexity will be similar, but there are a couple of rules, couple of I would say more differences from time complexity that we need to take care of. Okay. So first of all, the concepts are pretty much the same. Like the big O concept, we want to find an upper bound function which we will call big O in terms of space complexity. So all of that is going to work absolutely the same way. So for example, let's look at few codes and see what the space complexity for them will be. Right? For example, let's say I have a function which is supposed to print, if I give it n, I'm supposed to print numbers from 1 to n. Right, so I'll take I is equals to 1 while I less than equal to n. I will print I and I'll do I is equals to I plus 1. So now if you look at this code, right, you gave it an input that was n. Now I'm just creating one variable, one extra space, right, just one space for integer, and that is enough for me to execute the whole program. I don't need any extra space. So the space complexity here, space requirement is actually k, or you can write it k into n to the power 0, which basically we call big O of 1. It's a constant space requirement. We generally call it big O of 1, that it is independent of n, right? So that's how we'll find the space complexity in this case. Okay, now let me change this a little and we'll come to the first thing that you need to take care of while you are finding space complexity. Let's say I create j is equals to 0 here, right, for whatever reason. Now what is happening is you created I is equals to 1. Every time this loop is running, you are creating j is equals to 0. So in a way, the amount of memory that you are using is some constant k1 plus n times k2. I'm assuming this takes k2 space, this is taking k1 space. They will be same, but in general you could say that this is a string, this is an integer. So basically, like, they could potentially take different amount of space. So k1 for this space that you have used here, k2 for this space that you have created, and this space is getting created n times. So potentially I could say the total space requirement is k1 plus nk2. That would mean we can ignore this part because this is insignificant compared to nk2, and we would have said space complexity is big O of n. But this is wrong. This is wrong because the first time I go inside the loop, I'm creating a variable, I'm using some space. Now the next time when I come into the loop, I don't need the previous variable that I've created. What that means is I can reuse the memory that I had used earlier, or somebody else can reuse that, and I don't require a lot of space at any point of time. Let's say my program uses 8 bytes of memory. Next second it uses 8 bytes of memory, and it runs for 10 seconds. Let's say it uses 8 bytes of memory, then it uses 16 bytes of memory, then 4 bytes, and then it stays at 4. What do you think is the space requirement of my program? Is it 8 plus 8 plus 8 plus 16 plus 4 plus 4 and so on? I don't think so, right? Because I need 8 bytes. Then I'm using the same 8 bytes, or I have released those 8 bytes and I'm using some other 8 bytes. So at any point in time, I don't need more than 16 bytes. So in a way, my space requirement is only 16 bytes. If you give me 16 bytes, that's going to be good enough for my program to run, because that's the maximum space I would require at any point in time. So the point I'm trying to make here is, while you're calculating space complexity, it is maximum space required at any point in time. It does not mean that you add up all the memory requirement, you figure out, okay, I need 8 bytes right now, oh, I need 15 bytes now, I need 20 bytes now. So whatever is the maximum, that is your space requirement. And that makes sense, right? Just because Chrome is running on my system, it's taking, let's say, half GB of RAM. If it keeps running for 2 days, does not mean Chrome requires 1 TB of RAM. The space requirement is only half a GB, and that's what it has been using from last 1 day. So it doesn't need the space complexity we will calculate, that will be based upon the maximum space requirement at any point in time. So for this code, I need this memory, which is K1, and at any point in time I only need this memory once, that is K2. The next time I would need it, I don't need the previous one. So the space requirement is K1 plus K2, so it is actually big O of 1. It is constant space requirement. Okay, it is constant space requirement. On the other hand, if I had created a list and a list of, let's say, n size, that basically means you have created an array, a list of n size together, right? Like at one point of time you need this list of size n. That means you need this extra space of size n. In that case, your space complexity will become big O of n. Okay? So you need to be careful about while you're calculating space complexity, you need to be very careful that you are making sure that you are calculating the space requirement at any point in time. So this is the first thing you need to take care of. Not overall, at any point in time. The second thing that you need to take care of is you only count the auxiliary space. This is the extra space that you require. If I ask you, if I tell you, hey, take this array, sort it. Now obviously your algorithm needs this array to sort it. Unless I give it an input array, how will it sort that array? So if the algorithm is able to sort here itself, right, it does not require any additional array, or like if it requires only 4, 5 or 100, whatever, some constant number of variables, I should say constant number of variables, then my algorithm is big O of 1, because whatever space you gave me, whatever array you gave me, I am not using any extra space other than that except few constant number of variables. I am not creating another list of size n. If I am doing that, then the space complexity will change. But the input array that you have given me, don't count the input space requirement in your space complexity. Right? For example, in the next session we will look at bubble sort. Bubble sort takes an array and it changes the array here itself. It does not require any extra space other than 3-4 variables. It does not take a new array. It doesn't do anything that requires a lot of space. So space complexity of bubble sort will be big O of 1. It will not be big O of n, even though when you run this algorithm, obviously there will be an array of size n that will be passing around, but that is an array that bubble sort is not creating. It needs that array to sort it, right? You need to pass that array if you want bubble sort to sort that. So it's not bubble sort's mistake. We are not going to count that array into bubble sort's calculation of space complexity. So these two things you need to take care of. The third thing that you need to take care of is, if you are using recursion, recursion takes space. If I call Fibonacci 5, sorry, factorial 5, now factorial 5 does not return, it calls factorial 4. That in turn calls factorial 3, that in calls factorial 2, that in turn calls factorial 1, and so on. Doing all of this requires space. Now when you have reached factorial 1, factorial 5 is still sitting in memory somewhere, right? So this is not free, this takes space. So whenever you are using recursion, recursion requires some space. How to calculate this? We will see that in couple of sessions going forward. But these three things you need to take care of whenever you are trying to calculate space complexity. Okay, so in the next session we'll start looking at few examples and we'll start calculating the space complexity for them. Okay, thank you. Hi. So let's pick couple of easy algorithms which basically we can use to calculate space complexity. So I'm starting with pretty simple algorithms and let's find their space complexity. So the first one is bubble sort. I've already told you what is the answer for space complexity for this algorithm, but let's see what bubble sort does. Right. So I'm given an array. This space does not count in my space complexity. So I'm talking as if I am the algorithm. So as bubble sort, I'm given an array. So that array is not part of my space complexity. Now I need to maintain this I, which is where I am right now, right? So then I compare I and I plus 1 and then basically I swap if required, right? Along with that I would need another j, that is to make sure to remember how many elements are at their right place, right? So I need to do something multiple times. What is that I have to do? I need to compare elements and swap, Once I'm done with this, then I need to do this again. So I need couple of variables. Let's say maybe 3, 4, 5 variables. Again, constant number of variables. Even if I require 100 variables, that's fine. Constant number of variables is the key. So I need k space for all of this. And then I am not creating any array. I am not using any dictionary. I am not using any set. I am not using any kind of data structure to store any kind of data. Right? So it's very clear when you look at Babel sort algorithm that you just need some constant number of variables. You do not require any extra space. The total space requirement is k. So we say that the total space requirement is k into n to the power 0. That means algorithm is big O of n to the power 0. That means algorithm is big O of 1. Constant space requirement, big O of 1. Okay, so that's how we can calculate it for bubble sort. Now let's look at another example. Let's use factorial. So first of all, let's look at factorial iterative. So when you're finding iterative factorial, you take an answer, take it to be 1, you take an I, and you take something like this, right? Answer is equals to I into answer, and you return answer. Again, very straightforward. The whole code doesn't require more than 3-4 extra variables, and as soon as you have that, you require constant amount of space, and because you require constant amount of space, that basically means your space complexity is big O of 1. Now let's take something interesting. Factorial but recursive. Factorial but recursive. Right? Now let's say this is my function of factorial. So what do I need to do? Because it is recursive, I am going to check if n equal 0. I will return 1. Otherwise, I will return n into factorial of n. So in a way you will see I haven't created even a single variable. I don't even have a single variable, right? But the space complexity, sorry, n minus 1 here. But the space complexity of this function is not big O of 1. It is not big O of 1. That's because when you call factorial n, it calls factorial n minus 1. Can this function go away? Is its work done? No, it's not. Its work is not done yet. Then you call factorial n minus 1, factorial n minus 2. Still factorial n has to wait. It's not done yet. Eventually, you will reach factorial 1. Now when you reach factorial 1, all these functions are somewhere in memory and waiting for you. They have, all of them have their local variables. For example, each of these need to remember their n value. For this, let's say n is 10, for this n is 9, and so on. So all of them need to remember this value. Along with that, we need to remember which line we had reached while executing it. We need to do all of that, right? So a function is taking up some memory while it's waiting for recursion to complete its work. So when you have only one function, there is one function in memory. When it calls factorial n minus 1, there is another function in memory. When that calls factorial n minus 2, there are three functions in memory. At that point of time, when you reach factorial 1, that's the point where you have maximum number of functions in the memory, that is n functions. Actually, it will call factorial 0 as well. So n plus 1 functions are waiting in memory. Each of these functions is taking constant space, right? You have one local variable, along with that you have whatever function's address will be there, which line of execution it is. So all this is constant amount of space. So each function requires constant amount of space, but at the point when you reach factorial 0, there are n plus 1 functions which are waiting for you. Each function takes k space, so you are using k into n plus 1 memory. This is not constant memory, this is linear memory, linear in terms of n. So this basically means you have big O of n space complexity, right? And this is happening because you are using recursion, and recursion requires to store all these functions while they are waiting for the downward function to return back. Okay, so while they are waiting these functions to return back, all of these have to wait in memory, and that requires space. So we have to be careful while we are calculating space complexity for recursive functions. And obviously we will not be using recursive function for factorial, we will be using the iterative one. But the cases where we will be using recursion, there the space complexity might not be too bad, or it like the code that I am able to write using recursion might be too elegant compared to iterative one, that I am okay to compromise on a little bit of space, right? But definitely if I compare factorial iterative and factorial recursive, the time complexity is same, but the space complexity of recursive solution is much worse compared to the iterative one. Okay, so great. Please practice finding space complexity for a few more problems, iterative as well as recursive, and things will become a lot more clear. Okay, thank you. Hi. So in this session I want to find the space complexity for merge sort, right? So let's get started. Merge sort. So in case of merge sort, what were we doing? So we have this array, we are making two parts of it, right? So as soon as we entered the function, we created two arrays of n by 2 size. So n space is already used, right? So we are sure it cannot be bigger of 1 anymore, right? So it's using at least n space. Now what happens is we call merge sort on this function. So when you call merge sort on this function, this will internally create two n by 4 sized arrays. Similarly, this function will also create two n by 4 sized arrays, right? So this function created these two. When you call merge sort on this, it will create two. When you call merge sort on this, it will create two. So one common mistake that we can make is we can say that this level also takes n space. Now as soon as you say this, there is a problem in that. It is taking n space, right? Like n by 4, n by 4, n by 4, n by 4. But the problem is both these functions will not be called at once. First you will call this function, and once this function returns, only then you will call this function. So it's not true that there will be no point in time when all these 4 small arrays will be existing. Once you call this side, it will create these 2 small arrays. So they will be available in memory, but these 2 are still not created yet. And once you return from this array and you go into this part of the function, then you will create these 2, but by then these 2 have already been cleared, we don't need them anymore. So it's not that each level requires n space. So very common mistake everybody makes, what they say is first level requires n, second level requires n, third level requires n, fourth level requires n. How many levels are there? We have already discussed this in time complexity. So we had Tn, then we went to Tn by 2, Tn by 4, and we figured out that we need log n levels. So a common mistake that you can make is to say, hey, my space complexity is also n log n as was my time complexity. But that will not be correct, because all these arrays are not going to be in memory at any point in time. Right? They are existing at different points, and there will be no point when all of them are in the memory. So a better way to look at this is the original array. Now this created 2 small arrays. So n space is required for sure. So as soon as we entered, we created these 2 n by 2 sized arrays. So it's available. This is required. Now when you call on this function, it's going to create 2 n by 4 sized arrays. That means n by 2 space is required here. Right? At a time only one of these 2 functions can be there. Whichever function is there, it will create n by 2 space. Now only one of these functions will be in memory at any point in time. First you will call this, so the second function is not in memory, and once you return from the first, only then the second will be called. So only one of these will be in memory at any point in time. And when this function is in memory, it will create 2 n by 8 sized arrays. That means it requires n by 4 space. So as you can see, the pattern tells you that the total space requirement is n plus n by 2 plus n by 4 plus n by 8 up to, let's say, 1 or 2, whatever the last number is. Right? So this is the amount of space you require, which is equals to 1 plus half plus 1 by 4 plus 1 by 8. This part cannot be more than 1. This part is always less than equal to 1. So at max the space required will be 2n. It will not be n square, it will not be n log n, it will basically be 2n. Or you can say the space complexity is big O of n in case of merge. Right? In case of merge sort, the space requirement is big O of n. Okay? So that's how we can calculate the space requirement of merge sort. You need to just be careful that you understand how exactly recursion is working, how layer by layer recursion is working, right? First one function is called, then that is calling one more function, then that is calling one more function, and so on. That's how you're going, and at any level there can be only one function that is alive at any point in time. So in case of merge sort, maximum number of functions that you can have in your memory at any point of time is log n, because you have log n levels, so there cannot be more than log n functions present at any point in time, right? The space requirement is more than log n because each function is not storing constant amount of memory, it is storing some extra memory, and we added all that memory to reach our conclusion that the total memory requirement is 2n, which basically means we are big O of n in terms of space complexity. Okay, so that's how we are able to do for merge. Now you need to find for binary search as well as couple other problems. Please go through them, and like applying exactly whatever we have learned, you will be able to find space complexity for those problems as well. Okay, thank you. Hi. So in this session I want to talk about quicksort, right? So we have written the code for quicksort, but we haven't talked about the time complexity or space complexity for quicksort at all. So let's talk about quicksort. Quicksort is a little interesting, right? So quicksort says, so the way we discussed is, we said we will pick an element and we will use that element as a pivot element. We will find everything that is smaller than your pivot and we'll put that on the left side. Pivot will go to its right place, its correct place, and everything greater than or greater than equal to P goes to the right side. So that's how we talked about quicksort. In general, we will not be taking the first element to be pivot. We will take a random pivot. So we will calculate, we'll find a random number and we will use that index to be our pivot element. Okay. So it's not that we will always take the first element to be the pivot. We will pick a random number, a random pivot element and use that as our pivot. Okay. So if your list is of size n, then you create a random number from 0 to n minus 1 and then that index becomes your pivot index. Okay. So that's just one slide change that I want to tell you while we are calculating the space and time complexity. Okay. So now let's first talk about the partition algorithm. So let's say I have chosen a pivot. Now what is the time required to put the pivot at its right place and then put everything smaller than pivot to left and everything greater than pivot to the right. So let's find the time requirement of that particular part of the code. Okay. So first of all, we find a random number that's constant work that becomes our pivot. Now we go through all the numbers to find count of numbers less than p. We did this to find where should we move pivot to. So we have to go through the complete list to find count of elements that are less than p. So you have done k into n work here to decide where to put pivot. Once you put the pivot to the right place, then what did we do? We took an I, we took a j. For every iteration, we were either moving I or we were moving j, and sometimes we were moving both of them. So I is moving here, j is moving here, and eventually they will meet, right? So the total distance covered by a and j combined is going to be n, and every time one of them move, the only thing you are doing is checking, is this element greater than p or less than p? Is this element greater than p or less than p? So you're just doing constant work. Constant work tells you whether to move I or to move j or to move both of them. So in constant work, I am able to bring them closer and I need to do this constant work n times. So this actual partitioning work will take some other constant k2 into n. So this is the time requirement of the first part where we are finding the number of elements which are less than p, and this is the second part where we are putting everything less than p on left and everything greater than p on right. Total time requirement means some constant k into n. So this is for just the partitioning algorithm. This is not complete quicksort. Just the partitioning algorithm is taking kn time. Okay. Now let's talk about quicksort. See, the worst thing that can happen with quicksort is you pick a pivot and that pivot is the smallest element or the largest element. That becomes the smallest or the largest element. So your recurrence relation will become, this is for the partitioning algorithm. So Tn is Tn minus 1 plus Kn, because pivot has moved to the leftmost or the rightmost position. Now you need to sort these n minus 1 again. This is the worst case. And if this keeps happening, your time complexity will be big O of n square. Please solve this, and as you will solve, this is a very simple recurrence relation. As you solve this, you will figure out the time complexity will be big O of n square. So in the worst case, quicksort can perform as bad as big O of n square. In the best case, In the best case, what's going to happen is your pivot will go to the middle. Now as soon as your pivot goes to middle, this becomes Tn is equals to 2Tn by 2 plus Kn. This is for partitioning, and you have two smaller problems to deal with, and both of them will have size n by 2 in the best case, when you get a really good split. Now this is same as merge sort, the recurrence relation, and your algorithm will have time complexity of big O of n log n. So seems like in really good cases quicksort will work as fast as this. In extremely bad cases quicksort will work as bad as this, right? So quicksort can become as good as merge sort, and it can become as worse as bubble sort or selection sort. Okay. Then why is it called quicksort, right? So first of all, this is an example where we will not take the worst case into consideration while calculating time complexity. So when I started talking about time complexity, I said that we will be looking at worst cases in almost all the cases. This is one of the cases where we can actually look at not the worst case but some other case. Why? See, so here you getting a situation like this can happen by chance. It's not in user's control. User cannot decide that I'm going to give you an input like this. For example, if the user gives me this input, for quicksort, the user gives me this input, and I decide that the first one is going to be my pivot. If I decide that the first one is going to be pivot, then this will go to the rightmost, and then again I'll have these many problems like this bigger problem to deal with. Then again I'll get 9, which will be again a really bad split for me. So if I take the first element to be the pivot element, in that case I will have to say that the worst case is order n square and the time complexity is big O of n square. But now I am saying I'm not going to pick the first one. I'm saying I'm going to pick a random number, and that will become my pivot. So as soon as you say that I'll pick a random number and that will become my pivot, the user cannot control that you have to hit the worst case. Now you will hit the worst case not because the user wants it, you will hit the worst case if your luck is really bad all the times. And for a huge list, your luck is not going to be bad all the time. Whatever you feel about your luck, it cannot be that bad that you keep hitting either the leftmost or the rightmost, right? So that's not going to happen. So that's why there is a category of algorithms called randomized algorithms, where we add some randomization so that somebody from outside, somebody who does not know our code, somebody from outside is not able to give us an input which makes our algorithm perform really bad. Whatever input you give me, I am going to randomly choose some part of my algorithm such that the worst case is still n square, but the chances of hitting that worst case is basically depending upon that random number generation and not on the person who is giving me input. Okay, so in case of quicksort, because of this randomization, we will not assume that we will keep hitting case like this. Okay, so how can I assume that I'll always hit the best case? No, I will not assume that I'll always hit the best case. On an average, I can assume that my split will be something like this. Not the best case where n by 2 is happening, not the worst case where 1 and n minus 1 is happening. Even if I get a split like this, and if I get a split like this, my recurrence relation will be this. I am not going to solve this recurrence, but this is not that bad a problem to solve, right? So if you solve this recurrence, you will still get kn log n. The log base will be different, like log base will not be 2, but that again doesn't make much of a difference because you can convert it to log base 2, right? So this becomes very like similar to merge sort, right? So quicksort in the average case, I'm not talking about the best case, I'm not talking about the worst case, I'm talking about the average case. On average, quicksort is going to perform big O of n log n, right? So quicksort actually performs really well. In practice, it works really well, and we don't have to worry about its worst case because of this amazing concept called randomized algorithms. We've just added randomization, so now the user is not able to control how good or bad my algorithm is going to perform. It's basically about the random numbers that I'm generating, and like if you create these random number generation, like if you create these random numbers enough times, they will have a good distribution and you will not always hit the bad number, right? So the space complexity in the average case is going to be big O of n log n, okay? So the time complexity will be big O of n log n. Now let's talk about the space complexity, right? Now let's talk about the space complexity. So in case of quicksort, you get this array, you pick a partition, you move this, you pick a pivot, you move the pivot to its correct place, then you do the partition here itself. Everything is happening here, just using constant space. And then as we discussed, let's assume we do a 3/4 split here and 1/4 split here. And then again we do a 3/4 split here and then again 1/4 split here, right? And you keep going like this. Each function requires constant space. So now we don't have to find out how many functions will there be. That's not the right question. How many function calls are going to happen? What we need to find out is the maximum number of functions that we will have in our memory at any point in time. If you're finding space complexity, you should not look at the total number of space required. You need to look at any point in time, what is the maximum space required. So we want to know at any point in time what is the maximum number of functions that will be in memory. So how many functions will be there in memory at max? Okay, so we have one function, then we have one more function. Let's look at this 3/4 side of the functions. So you had n elements, then you have 3/4 n, then you have 3/4 square n, and you will keep going till you have only one element. So if you have x functions, that basically means exactly same logic as we have discussed earlier. After one level it becomes 3/4 n, after two levels it becomes 3/4 square n, after x levels it will become 3/4 x n, and that has to be equal to 1, right? That has to be equal to 1. So this basically means n is equals to 4/3 x. Let me clear it. Which means x is equals to log base 4/3 n, right? So in case of merge sort, we got log base 2n. If you want to convert to something similar, x is going to be, using the formula of logs, you can say log base 2 4/3, right? So I'm using this formula. Right, this is the formula that I'm using here. So this was log base 4/3, so this becomes this comes in denominator and this stays in the numerator. This basically means x is equals to 3.47 log base 2n. So in case of merge sort, these were the number of times you had to run it. This was the depth of recursion. In case of quicksort, on an average case, this will be your depth of recursion. Still, this is a constant. So basically, the number of function that will be in memory is this much, but that is again big O of log n. So these are the number of functions that you will have in a memory. Each memory is going to take constant space. Each function is going to take constant space. So the total space requirement is big O of log n. Okay, it's big O of log n. So basically that proves that quicksort is big O of n log n and big O of log n in terms of space. So this is time and that is space, and we are looking at the average case. In the worst case, things can be worse, things can be bad, but because of randomization in quicksort, we will look at the average case instead of looking at the worst case. Okay, perfect. So I hope the quicksort is very clear to you, like what exactly, what was the, why did we allow quicksort to look at average instead of looking at worst, and how did we find the average case time complexity and space complexity in case of quicksort. Okay, perfect. Thank you.